It's been 7 days since perihelion November 5th, 2025. Across global observatories, Object 3I Atlas has begun acting unlike any known interstellar visitor. Data collected since October 29th reveal an unexpected surge, a sudden violent brightening that defied every prediction. Its luminosity climbed far beyond what thermal projections could explain. For a short interval, instruments aimed near the sun recorded not chaotic flickers, but a patterned pulse of light. Responding fast, ESA and NASA teams switched into emergency observation mode. Solar coronagraphs captured a faint, elongated halo forming around the object, thin, nearly invisible, yet stable for hours. What should have been a simple rise in reflective dust instead appeared structured, layered, as if something inside 3I Atlas had fractured. Whether by internal force or deliberate design, spectral analysis detected emissions of carbon dimer, ammonia, and hydroxyl compounds, but without the expected dust signature. And that missing dust trail was what unsettled scientists most. In every natural outgassing event, vapor and dust appear together. This time, only vapor remained. When 3I Atlas reached its closest point to the Sun on October 29, 2025, astronomers expected a routine display, a predictable surge in brightness as it neared perihelion, followed by a rapid dimming as it drifted away. Instead, what unfolded over the following days forced scientists to rethink the fundamentals of interstellar comet behavior. Within just 48 hours, the object's brightness didn't fade. It intensified, nearly doubling, and forming an extended plateau of luminosity that no existing thermal model could explain. This remarkable event, now known as the perihelion brightening anomaly, has become one of the most puzzling astronomical phenomena of the decade. At first, researchers suspected a calibration glitch. The initial photometric readings seemed off. An unexplained 0.8 magnitude increase appeared inconsistent with expected post-perihelion trends. Yet, data cross-verified from independent observatories quickly dismissed that theory. The La Sombra Observatory Network and Japan's Subaru telescope both confirmed the readings. Against all norms of cometary physics, the object continued to grow brighter even as it moved away from the sun. Ordinarily, comets peak in brightness before perihelion, when solar heat drives intense sublimation, the process of volatile ices turning into gas. After this point, they cool, activity wanes, and the glow fades. But 3I Atlas defied this rule. On November 1st, the European Southern Observatory released its early data, revealing that the object's brightness had doubled within just 2 days. Yet, despite this surge, there was an eerie absence of dust. Instruments from the Lowell Discovery Telescope detected significant gas emissions, particularly in cyanogen and hydroxyl bands, but polarimetric analysis showed almost no increase in light scattered by dust particles. This discovery meant that the observed luminosity wasn't from reflective dust, but from gas molecules fluorescing under intense sunlight. For comet scientists, that revelation was profound. A gas-dominant brightening meant 3I Atlas was venting volatile compounds directly into space, without ejecting solid fragments. Its internal makeup and surface composition were likely nothing like any comet known to have formed within our solar system. A November 3rd report from the University of Maryland's Comet Research Group noted that the ratio of gas to dust emissions was more than 20 times higher than that of typical Oort cloud comets observed at comparable distances. Meanwhile, at the Harvard-Smithsonian Center for Astrophysics, teams ran thermal stress simulations using the known orbital and rotational data. The results suggested a maximum surface temperature near 230 Kelvin, sufficient to vaporize carbon monoxide and carbon dioxide, but far too cold to explain the intense water vapor emissions being recorded. This suggested something extraordinary. The object's interior was preconditioned, possibly by millennia of cosmic ray bombardment, which could have hardened its crust while trapping volatile materials deep below. When sunlight finally penetrated that crust, the trapped gases may have escaped explosively. Yet, the gradual shape of the brightness curve ruled out a single violent outburst. Instead of a sharp spike followed by decay, 3I Atlas's luminosity increased steadily, plateaued, then faded slowly. Astronomers at the Instituto de Nereidas described this as a controlled evolution, a term that immediately sparked debate. Some argued this indicated self-regulated venting, with gases escaping through sequential fractures as the object rotates. Others believed it to be a coincidence, the result of a complex mix of rotation, composition, and solar heating. The most striking visuals came from NASA's Solar and Heliospheric Observatory. Its LASCO C3 coronagraph captured 3O Atlas as an asymmetric, elongated glow gliding across the inner solar system. In time-lapse sequences, the coma appeared to stretch along its path, forming a narrow, filament-like tail, an unusual sign. Unlike the broad, fan-shaped tails typical of natural comets, this one appeared linear and focused, as if the emissions were channeled into a directed stream, rather than a diffuse plume. Further evidence came from the Solar Orbiter spacecraft, which happened to have an ideal viewing angle during the event. Its SWA instrument detected fluctuations in local plasma density as the object passed nearby, implying that the vented gases were interacting with the solar wind in an unusually organized manner. The data hinted at coherent, collimated gas flow, not random ejection. When the Royal Astronomical Society published these readings, one reviewer noted that the symmetry of the emissions resembled an artificial venting pattern, rather than a chaotic one. While mainstream astronomers dismissed such speculation as premature, consensus formed around one truth: the mechanism behind the brightening remained unexplained. Currently, 3 leading models are being debated. The first, the subsurface pressure burst hypothesis, suggests heat buildup beneath an insulating layer caused trapped gases to erupt. The second, the layered sublimation model, proposes that alternating strata of volatile and refractory materials vaporized sequentially as sunlight penetrated deeper. The third, newer model, the electrostatic discharge hypothesis, posits that intense solar radiation ionized the surface, releasing energy through plasma-driven erosion instead of traditional thermal sublimation. Each theory explains part of the mystery and fails elsewhere. The pressure burst model accounts for sudden venting, but predicts a short-lived flare, inconsistent with the sustained plateau observed. The layered sublimation theory matches the gradual rise, but not the extreme gas-to-dust ratio. The electrostatic model fits the spectral data, but doesn't yet explain the massive water vapor spike detected by the Atacama Large Millimeter Array, ALMA, nearly 40 times the pre-perihelion baseline. A joint team from NASA's Goddard Space Flight Center and the European Space Agency is now analyzing all available data under an initiative called the Interstellar Object Watch. Preliminary findings presented at the Planetary Defense Conference suggest that 3O Atlas might have experienced a partial surface collapse, similar to an ice crust fracturing over a buried reservoir. If so, the event would be natural, though exceedingly rare. Still, ESA researchers warned that the remarkable symmetry of the brightening pattern didn't match a random breakup. If 3O Atlas had fractured unevenly, its brightness would have fluctuated irregularly as jets vented from isolated points. Instead, luminosity increased uniformly across multiple hemispheres, implying the entire surface released gas almost simultaneously. Such synchronicity suggests either an exceptionally homogeneous internal structure or a slow, deliberate rotation that exposed each region to sunlight in turn. The current rotation period of the object, measured at approximately 8.6 hours, lends support to the possibility that its unique activity may be influenced by its rotational dynamics. Meanwhile, a growing number of amateur astronomers, equipped with medium-sized telescopes, have continued to track 3I Atlas as it drifts outward beyond 1.4 astronomical units from the Sun. Their recorded data, shared through the Minor Planet mailing list, reveals something remarkable. The comet's brightness is stabilizing, yet remains higher than any forecasted model predicted. Even a week after perihelion, 3I Atlas continued to shine brighter than any interstellar visitor observed at a comparable distance. That fact alone implies one of two things: either the object possesses an exceptionally volatile composition, or an unknown reflective mechanism is at work within its expanding coma. By November 5th, consensus had formed among leading observatories worldwide. 3I Atlas had not exploded in the conventional sense. Rather, it had undergone an event that transformed its reflective and emissive behavior in ways not previously documented. Whether triggered by a thermal cascade, structural venting, or an entirely new physical process, the aftermath has challenged long-held models of how ancient interstellar material responds to solar radiation. As data from observatories across 3 continents converged that same morning, one conclusion stood out: 3I Atlas expelled vast quantities of gas during its perihelion passage. but released virtually no dust. For seasoned comet researchers, this combination borders on impossible. Normally, when sunlight strikes a comet's icy surface, it vaporizes the ice, lifting dust grains into space and forming the familiar glowing tail. But in this case, instruments detected a powerful gas signature with no accompanying dust signature whatsoever. The Subaru telescope spectrometer recorded distinct absorption lines for carbon dimers, ammonia, and hydroxyl radicals, all consistent with the decomposition of volatile ice. Yet its polarimetric readings showed a sharp absence of scattered light, indicating a near-total lack of micron-sized dust particles. This extraordinary result was soon independently verified by both NASA's Infrared Telescope Facility and the Hubble Space Telescope. Such a dustless environment led to a striking theory: 3I Atlas might be coated by a dense, compact surface layer that prevents solid particles from escaping. Supporting this idea, the James Webb Space Telescope, JWST, already observing the object in the mid-infrared, detected strong emission lines of water vapor, ethane, and faint traces of methanol, all emerging from a tightly confined region near the nucleus. Yet JWST's thermal curve revealed something even stranger. The temperature of the coma remained unusually low. The gases were venting cold, implying that the release wasn't caused by direct solar heating, but rather by internal pressure or chemical reactions occurring beneath the crust. Although rare, the phenomenon of gas-rich dust-poor comets isn't entirely unheard of. A few examples exist within our solar system, such as 96P Immaculs and Cethon 2016 R2, Pan-stars, both known for their high gas-to-dust emission ratio. However, even these do not approach the extreme purity seen in 3I Atlas, where the ratio is almost absolute. At perihelion, telescopes observed no continuum scattering at all, confirming that the gases escaped independently, without carrying any solid particle. To unravel this mystery, researchers turned their attention to the comet's surface chemistry. A team at the European Southern Observatory proposed that over millions of years of cosmic radiation, the outer layers of 3I Atlas had been compacted into a tar-like organic crust. Similar to how radiation can transform simple ices into complex hydrocarbons, this hardened layer may be both dense and cohesive, sealing interior volatiles beneath. When sunlight penetrated these toughened layers, only the trapped gases below could seep through, leaking via microscopic fissures without dragging dust with them. This interpretation aligned neatly with JWST's mid-infrared data, which showed spectral features consistent with long-chain hydrocarbons, materials that only form after prolonged radiation exposure. Meanwhile, at the Planetary Science Institute, another research team suggested a deeper origin-based explanation. If 3I Atlas had formed in a different interstellar environment, possibly around a red dwarf star with an unusual elemental composition, then its primordial ices might inherently contain fewer silicate grains and higher volatile content than solar system comet. In that scenario, what astronomers are witnessing could be the chemical fingerprint of its birthplace. Indeed, the carbon-to-oxygen ratios extracted from JWST's spectral data differ subtly from any known solar system comet, suggesting a chemical evolution shaped by conditions alien to our neighborhood. However, this dust-poor event created practical difficulties for scientists. Without dust to scatter sunlight, optical telescopes struggled to estimate the object's size and rotation rate. Normally, variations in reflected light help determine surface irregularities and rotation. But in this case, researchers had to rely entirely on gas emission fluctuations, detected through high-resolution spectroscopy. From this, early analyses indicated a rotation period of roughly 8.5 hours, consistent with small oscillations seen in its light curve. Yet an even more intriguing layer of mystery emerged when Solar Orbiter's magnetometer detected a faint magnetic field disturbance, coinciding with the gas eruption. This disturbance, a localized ripple in the solar plasma, hinted that the escaping gas might have been ionized and interacting with the solar wind in an unusually structured, possibly directed manner. Unlike the wide, irregular plasma tails typical of comets, this signal appeared narrow and precisely aligned with the object's trajectory. That pattern suggested a jet structure guided by magnetic or electrical forces, rather than random outgas. As a result, planetary scientists have revived interest in older, once-dismissed theories of electrochemical comets, celestial bodies where charged particle dynamics trigger volatile release without traditional heat-driven sublimation. According to one revived hypothesis, high-energy cosmic rays could have gradually built up trapped charge zones within the object's crust. When sunlight reached those layers, sudden electrostatic discharges may have unleashed both energy and gas, explaining the comet's bright, dust-free emission. Skeptics, however, remain cautious. They argue the simplest explanation may still hold true. 3I Atlas might simply be composed of extremely fine-grained ice that vaporizes directly into gas, without forming cohesive dust aggregate. In that view, its dramatic brightening was triggered by a rapid phase transition, shifting from dormancy to intense activity the moment solar energy reached deep enough layers. Such behavior has been observed in carbon dioxide-dominated comets, which only activate once specific thermal thresholds are breached. Yet even among those, none have displayed the sheer scale or symmetry of the event seen in 3. The flare produced by 3I Atlas exceeded every recorded CO2-driven event in modern observation. In the days after its close solar pass, ultraviolet tracking from multiple observatories revealed a strong hydroxyl emission line near 309 nanometers. Clear evidence of water molecules splitting apart under solar radiation. Curiously, there was no corresponding scattering from solid debris, reinforcing the idea that gas was venting cleanly without accompanying dust. The missing silicate features, which would normally betray the presence of mineral grains, confirmed it beyond doubt. For planetary scientists, this presented a remarkable twist. If interstellar visitors can release gas without producing dust, our entire detection strategy may be flawed. Most survey telescopes identify active comets and small bodies by the sunlight they reflect off suspended dust. But a dustless, gas-emitting wanderer could slip through our instruments unseen. Invisible light, detectable only in infrared or radio bands. That possibility adds urgency to every ongoing observation of 3I Atlas, while it remains within range. As of November 5th, researchers are pushing every telescope they can to its limits. NASA's James Webb Space Telescope continues scanning its infrared glow, while Hubble prepares a new imaging sequence to check for any delayed dust emergence. So far, none has appeared. The coma remains unusually clear, thin, and sharply contoured, more like a transparent mist than a typical fuzzy cometary halo. It's as though the object carries a veil of vapor instead of a cloud of debris. In the hours right after its perihelion flare, solar observatories studying the inner heliosphere captured a now iconic image. A long asymmetric glow trailing behind 3I Atlas as it curved past the sun. At first glance, it seemed like a standard cometary coma, a hazy halo formed as sublimating ices release gas and dust. But this one was strikingly different. The glow was narrow, stretched, and distinctly one-sided, more a stream or wake than a symmetrical halo. It persisted for nearly 8 hours before fading, and that endurance hinted at something exceptional. The solar and heliospheric observatories' LASCO 3 coronagraph provided the clearest time lapse. Between 08:00 and 16:00 UTC on October 30th, the glow elongated into a slender plume around 5 times longer than the visible diameter of the nucleus. Yet brightness increased dramatically on one side while the opposite remained dim. This imbalance suggested that the venting wasn't uniform. Instead, gas appeared to be funneled through a focused channel as if escaping from a single jet or fracture. Frame-by-frame analysis revealed subtle rhythmic fluctuations in the plume's brightness, a pulsing pattern, suggesting intermittent bursts rather than constant outflow. That rhythmic emission prompted early comparisons to rotational venting, where a rotating body periodically exposes an active vent to sunlight. But when researchers compared the pulse timing with the estimated 8-hour spin period of the nucleus, the numbers didn't match. The outgassing rhythm was slower, closer to 12 hours. This mismatch implied one of two things. Either 3I Atlas's spin slowed dramatically during its solar pass, or some unknown internal or electromagnetic mechanism was modulating the flow. Meanwhile, NASA's solar orbiter, positioned about 60 million kilometers away, offered a second angle. Its coronagraph detected a faint perpendicular plume, a short, vertical streak visible only in extreme ultraviolet. This secondary jet lingered for 2 hours before fading, possibly as the object's orientation shifted. Together, the twin plumes created an eerie symmetry, intersecting trails that made the coma look almost engineered, as if twin exhaust streams crossed at the core. No one suggested the emissions were controlled, of course. but the geometry was unlike anything previously seen from a natural object. To explore how such structure could arise, scientists turned to advanced gas dynamics simulation. A research team at the Max Planck Institute for Solar System Research modeled the scenario using the known spin rate, solar flux, and nucleus diameter, estimated between 800 meters. Their simulations showed that if a hardened outer shell fractured along a longer longitudinal fault, sunlight could periodically heat the crack, producing a narrow, collimated jet. Multiple parallel fractures could combine to generate an elongated, stable plume, consistent with what telescopes observed from Earth. But the model didn't explain everything. Even as 3I Atlas moved away from the Sun, the plume maintained its integrity longer than expected. Under normal solar wind conditions, gas tails diffuse rapidly, spreading into faint wisps. Yet here the structure stayed coherent, suggesting that the molecules had been ionized and confined by magnetic field. Supporting that theory, the solar orbiter's magnetometer recorded a sharp fluctuation at the same time the extended plume emerged, hinting that plasma forces might be shaping the flow. While plasma tails are common among active comets, this one stood out. The plume's direction didn't align with the usual solar wind flow lines. Instead, it angled several degrees off-axis, pointing roughly along the object's trajectory rather than away from the Sun. That deviation baffled heliophysicists. One hypothesis proposes that 3I Atlas carries a faint intrinsic magnetic field, possibly acquired during eons drifting through charged interstellar regions. Such a remnant field could locally steer ionized particles, forcing them to travel independently of solar wind alignment. Meanwhile, optical data from the Las Cumbres Observatory network revealed yet another anomaly. The coma displayed a faint reflective sheen confined to a narrow wavelength range near 50 nanometers, consistent with metallic or mineralized grains, possibly sodium or magnesium compound. Though sparse enough to evade dust detection thresholds, their presence subtly tinted the plume with a faint green hue under sensitive filter. If verified, that would mean the gas escaping 3I Atlas wasn't perfectly pure. It carried traces of embedded refractory material, likely remnants from its crustal layers. Further modeling by JAXA's Solar Observation Unit reinforced this interpretation. Their simulations showed that a venting jet containing ionized vapor mixed with metallic particles could maintain a narrow, stable column via electromagnetic. In that scenario, the charged components interact to create a self-stabilizing sheath of plasma, a dynamic barrier preventing the plume from dispersing, preserving its ghostly needle-like shape across millions of kilometers. The resulting image matched precisely what telescopes had recorded, a thin, persistent beam of light, perfectly aligned with the object's path through space. By November 1st, several research groups had already released preliminary reports suggesting that the extended coma didn't necessarily indicate a breakup or explosion. Instead, it might represent a carefully phased pattern of venting governed by the object's orientation and exposure to solar heat. As sunlight penetrated deeper into its surface, multiple vents may have opened in sequence, creating symmetrical streams that gradually merged into one elongated plume. If the outer shell contained organic compounds altered by radiation, substances that act as thermal insulators, they could have delayed the release of trapped volatiles until the body rotated into a specific alignment, yet not everyone was convinced. Scientists at Caltech's infrared laboratory urged caution, noting that data collected near the Sun are notoriously tricky to interpret. Intense glare, scattered light, and background plasma distortions can easily create visual illusions. The elongated form might be nothing more than a projection effect, a standard gas tail seen from a particular angle, appearing narrower as it crosses a bright solar backdrop. To verify this, astronomers are waiting for follow-up observations from ground-based telescopes as 3I Atlas moves farther from the Sun and its viewing geometry shifts. What's clear for now is that the object's shape and structure have added an entirely new layer to the mystery. Up to this point, attention had centered on its unusual chemistry, its composition, its clean emissions, and the strange absence of dust. But now its physical form has entered the discussion. A narrow, well-defined coma suggests not a chaotic eruption, but a structured, repeating system of venting, a behavior more mechanical than random. That realization has prompted some scientists to reconsider what the crust of 3I Atlas might really be like. Could long-term radiation exposure have etched symmetrical fault lines that crack in predictable ways under heat? Or perhaps the body's own physical properties, its spin rate, density, and internal layering, produced a kind of self-reinforcing feedback loop. Just as astronomers were preparing to see the emissions fade, something entirely unexpected happened. This time, the anomaly appeared in the spectral signatures of water vapor. Instruments from the Atacama Large Millimeter Array picked up a massive jump in the 556.9 GHz line, the hallmark of hydroxyl production, a direct sign of sunlight breaking apart water molecule. Over just 2 days, the inferred water output rose nearly 40-fold compared to its earlier baseline, and remarkably, the surge persisted through the first week of November. Simultaneous observations from Hawaii, Chile, and Spain confirmed the trend. Spectral lines deepened, showing strong oxygen absorption bands and widening hydrogen emission features, clear proof that enormous quantities of ice were transforming into vapor. But the numbers didn't add up. Temperatures across the coma hovered around 200 Kelvin, far too cold for such vigorous activity. This meant the water wasn't boiling off the surface, but erupting from internal pressure, likely driven by trapped volatiles transitioning between phases. To explore this puzzle, planetary scientists turned to models of buried ice reservoirs. If 3I Atlas had spent millions of years drifting through interstellar space, its exterior would have hardened into a dark, carbon-rich crust, thickened by radiation exposure. Beneath that shell, volatile ices, water, carbon monoxide, ammonia, could remain sealed under extreme pressure. When the crust fractured during perihelion heating, sunlight would have reached those subsurface pockets, triggering violent sublimation. The resulting jets would erupt through fractures, releasing steady streams of vapor that appeared continuous when viewed from afar. Data from the James Webb Space Telescope's mid-infrared spectrometer added weight to this theory. Between October 30th and November 3rd, Webb recorded strong emission bands from H2O, CO2, and CH3OO, while the overall brightness barely changed. The ratio of these lines indicated that the gases originated deep within the nucleus rather than from surface ice. In essence, the sun's heat had peeled away the object's outer layers, exposing primordial material untouched since before the solar system existed. Even so, major discrepancies remain. The measured water output far exceeds what simple energy balance models predict. According to the European Space Agency's preliminary analysis, the total solar energy absorbed by 3I Atlas during perihelion could account for only about 1/10 of the detected vapor flux. That imbalance suggests another energy source must be at play, perhaps an internal heat reservoir, radioactive decay, or even a chemical reaction triggered when fresh ice first encountered sunlight after eons in darkness. One hypothesis involves buried carbon monoxide and methane reacting with oxidized minerals in the crust. When exposed to solar radiation, these compounds could spark mild oxidation cycles that release additional energy, freeing trapped water molecules in the process. Laboratory tests at the Southwest Research Institute show that such reactions can sustain vapor output far beyond what sunlight alone can produce. If 3I Atlas harbors similar chemistry, that would neatly explain both the intensity and the endurance of the water surge. Another explanation gaining traction centers on structural collapse. As the outer layers fractured, high-pressure ice pockets might have destabilized, collapsing inward and exposing new volatile surface. Each implosion could open fresh channels for sublimation, creating a continuous-looking rise in emission even though the events were local and discrete. The object's light curve supports this. Small peaks are superimposed on a larger upward trend, consistent with repeated bursts of venting rather than a single sustained release. But a more unconventional idea is also emerging. Some researchers point out that the timing of the water spike roughly 12 hours after the elongated coma reached its peak might hint at delayed heating beneath the surface. If sunlight passed through the newly formed plume and was refracted or scattered back onto the nucleus, it could have concentrated energy into specific regions, accelerating sublimation from within. This feedback loop might have triggered a runaway reaction, where deeper layers vaporized suddenly, releasing massive volumes of water without increasing the surface temperature. Though speculative, the timing fits almost perfectly, It also helps explain why dust levels remained abnormally low. If the escaping vapor vented through narrow pores instead of broad ruptures, it wouldn't have lifted solid grains, producing clean jets of gas with minimal debris. In effect, 3I Atlas may have behaved less like an exploding comet and more like a venting geyser. By November 4th, the Hubble Space Telescope joined the campaign to map the expanding cloud. Ultraviolet imaging showed hydroxyl emissions spreading outward into a sphere nearly 50,000 kilometers across, encasing the faint nucleus in a vast, transparent shell. Despite its expansion, the cloud maintained an astonishing uniformity. No filaments, no clumps, just a smooth, consistent glow. For scientists, that symmetry proved almost as perplexing as the eruption itself. It implied that the release was evenly distributed across the object's surface, or that the escaping gas had reached a strange state of equilibrium after venting into space. Researchers at the University of Arizona suggested a process called photochemical recombination might be the key. As sunlight split water molecules into hydrogen and hydroxyl, a portion of those fragments immediately recombined, sustaining a delicate balance that kept the brightness remarkably uniform. This mechanism could also account for the coma's consistent appearance, even as it expanded. However, such stability would demand a nearly perfect interplay of temperature and radiation, a highly improbable coincidence, unless some natural self-regulating process was at work. Meanwhile, the burst of water vapor subtly altered the surrounding solar environment. Instruments aboard NASA's Parker Solar Probe picked up a faint but distinct increase in local hydrogen density as it traveled near the ecliptic plane in early November, though not definitively traced to 3I Atlas. The timing was too close to ignore. If confirmed, it would mean the object's emissions were powerful enough to influence the solar wind across hundreds of thousands of kilometers, an extraordinary feat for any comet, let alone one arriving from interstellar space. This discovery fueled a pressing question: what did the spike reveal about the interior makeup of 3I Atlas? Every data point pointed toward a layered body, a dark radiation-scorched crust beneath which lay a transitional zone rich in organic compounds, and deeper still, a pristine icy core preserved since the object's birth. The sudden eruption of water likely marked the moment when the crust cracked, exposing that ancient core to sunlight for the first time. In doing so, it granted humanity an unprecedented chemical snapshot of material forged in another star system. Yet, not everyone in the scientific community agreed with that interpretation. Some argued that the water readings might be distorted by interference from solar background emissions, or by overestimations in molecular fluorescence. Others noted that similar spikes had occurred when solar comets fragmented, a possibility still under investigation. If 3I Atlas had broken apart near perihelion, the exposure of fresh icy surfaces could easily have triggered the surge. But so far, telescopic observations revealed no separate fragments. The nucleus remained whole, implying the object had survived whatever had caused the burst. By the end of the first week of November, the water release began to stabilize, though it remained dramatically higher than pre-outburst levels. The prevailing consensus now defined the event not as an explosion, but as a global activation, a point where the object crossed a critical thermal and structural boundary, unveiling its inner layers to the sun for the first time. What had started as a mere flicker of brightness had evolved into the most complete chemical portrait ever captured of an interstellar visitor. Yet even as the outgassing continued, the James Webb Space Telescope detected something far more revealing. Beneath the luminous haze, faint thermal irregularities hinted at complex internal layering, zones of contrasting temperatures that might expose how the crust evolved under cosmic radiation. If those readings held true, they could explain not just the water spike, but the object's entire chain of peculiar behaviors since its arrival. Throughout early November, JWST continued monitoring 3I Atlas, with its mid-infrared instrument recording thermal emissions between 10 and 20 microns, a range ideal for mapping temperature gradients across both the coma and nucleus. What emerged from the data reshaped the conversation completely. Instead of a smooth thermal curve typical of most comets, 3I Atlas displayed abrupt temperature breaks, warm pockets surrounded by cold voids. The nucleus itself showed two distinct layers, a thin, sun-warmed shell, and a much colder inner body. That split was unexpected. It implied that while the surface absorbed sunlight efficiently, it conducted almost none of it inward. The crust, in essence, acted as a near-perfect insulate. When scientists at the Space Telescope Science Institute analyzed the data, they estimated the insulating layer's thickness to be roughly 50. Beneath it, the core's temperature was nearly 30 degrees lower than expected, a discrepancy only explained by the presence of a dense radiation-hardened crust formed over millions of years, as cosmic rays battered the object during its long interstellar voyage. Such crusts aren't just theoretical. Laboratory studies have shown that when ices rich in carbon monoxide, methane and ammonia are exposed to high-energy radiation, they gradually polymerize into dark tar-like compounds known as tholins. Over time, this residue thickens, hardens, and becomes remarkably heat-resistant. On 3I Atlas, that process likely continued for eons, sealing its inner ices beneath a rugged organic shell, capable of surviving temperatures that would obliterate most comets. This explains its strange delay at perihelion, why it remained quiet until sunlight finally penetrated its deepest fractures. Once those cracks opened, trapped gases burst out all at once, producing the immense flare and water spike observed after October. Infrared spectra from JWST also identified absorption lines belonging to aromatic hydrocarbons, intricate ring-shaped molecules that form only under long-term radiation exposure. These compounds were concentrated near the surface and rapidly diminished with depth, revealing a distinct chemical gradient. That pattern indicated that 3I Atlas's outermost layers were ancient and heavily processed, while its deeper ices remained untouched and pure. For planetary chemists, that insight is monumental, a direct glimpse into the molecular blueprint of matter shaped around another sun, long before the solar system's birth. The composition of its crust also explained why its coma carried so little dust. Over time, radiation likely fused the silicate grains into a compact matrix. When sublimation finally began, gas could escape through microchannels without dragging solid particles along, producing the dustless emissions seen during the outburst. Even more fascinating were the subtle variations in infrared brightness across its surface. JWST imaging revealed scattered hotspots among cooler patches, regions that seemed to correspond with known fracture zones, where sunlight may have reached deeper pockets of trapped ice. Their alignment matched the elongated coma seen in earlier optical images, suggesting that the outgassing plumes originated from those same weak spots. Some scientists now suspect these fractures act like natural thermal valves. As internal pressure builds, gas escapes in sharp bursts, rapidly cooling the crust and resealing the vent until the cycle repeats. This rhythmic venting could explain the comet's steady but pulsed brightness after perihelion, a signal far too consistent to be random.
At Harvard's Department of Astronomy, Avi's research group took a bold step in interpreting the James Webb Space Telescope's latest findings. After carefully analyzing the data, they proposed a provocative hypothesis that 3I Atlas's outer crust might act almost like a self-regulating shield. Over countless millennia, cosmic radiation could have gradually altered the crust's electrical properties, giving it the ability to store and release static charge. When sunlight struck the surface, localized discharges might have punctured the hardened shell, venting gas in rhythmic pulses. Avi Loeb emphasized that this didn't imply anything artificial. There was no suggestion of deliberate design, but rather that an unknown electrochemical process could be at work, one that naturally evolved on ancient interstellar objects. Still, the idea divided the scientific community. The conservative perspective considered 3I Atlas a purely natural relic, an ancient traveler whose radiation-forged shell had merely postponed its awakening. But a more daring camp believed the object's behavior was too structured, too synchronized, to be entirely random. Both sides, however, agreed on one crucial point. JWST had revealed the clearest evidence yet that interstellar bodies possess complex geological and chemical histories, unlike anything found within our own solar system. This revelation, the discovery of a multi-layered, electrically active crust, carries enormous implications for the future of space exploration. Any mission attempting to sample material from a similar interstellar object would have to bore through dozens of meters of radiation-hardened organics before reaching the untouched ices below. This knowledge will directly influence the engineering of next-generation probes, especially those designed to capture interstellar dust or collect high-speed flyby samples. But for now, the most immediate mystery remains unresolved. How exactly did that crust react during the perihelion flare? Did it rupture all at once, a sudden global break, or did it melt and vent from within as solar radiation triggered internal chemical reactions? The answer could determine whether 3I Atlas experienced a spontaneous natural outburst, or something closer to a large-scale structural failure. To uncover the truth, scientists turned to a subtle clue hidden in the timing and shape of the flare itself, the precise instant when brightness peaked and heat distribution shifted across the body. The data revealed something extraordinary, a rapid, synchronized change across multiple wavelengths, as though the entire surface responded in perfect unison. It all began at 60. At that exact moment, NASA's ESO coronagraph, ESA's solar orbiter, and numerous Earth-based observatories captured the same phenomenon, a sudden flash of visible light, lasting less than 2 minutes. No debris, no fragmentation, no shockwave in the plasma. Yet the object's total brightness spiked dramatically, and its spectral lines shifted in intensity across every instrument that observed it. To a casual observer, it would have appeared as a faint flicker, a heartbeat of light beside the sun's glare. But to astronomers, it was something far stranger, a global, perfectly synchronized pulse. In the hours that followed, instruments tracking 3I Atlas detected another baffling development. The surface temperature distribution, previously stable, had reversed. The cooler core suddenly warmed by about 20 Kelvin, while the outer crust cooled, and the transition occurred almost simultaneously across all visible regions. That meant the reaction wasn't localized. It propagated throughout the entire body, as if an internal shock wave had rippled through its structure. Infrared readings from JWST captured this sequence in extraordinary detail. Just before the flash, the spectrum displayed faint water signatures and a flat thermal curve. Moments later, water emission lines surged, joined by pronounced spikes in carbon dioxide and cyanogen. The shape of the new curve indicated that the gases had been expelled at high velocity, around 800 meters per second, before settling into equilibrium. And still, the object itself showed no signs of damage, no visible cracks, no debris trails. Its silhouette remained unbroken. Because of this, astronomers dubbed the incident the perihelion shock, a full-body reaction that looked explosive, yet left the object structurally intact. Theories emerged swiftly. The first explanation involved a rapid phase transition within the crust. Under extreme solar heating, amorphous water ice can suddenly crystallize, releasing trapped gases and latent heat in the process. That transformation could, in theory, generate enough pressure to account for the brief luminosity spike observed by ESO. But the numbers didn't add up. The volume of gas required to produce that much light was far greater than the amount the crust could release through crystallization alone. That led to a second hypothesis from plasma physicists analyzing solar orbiter data. During the same brief flash, the spacecraft's magnetometer recorded a sudden sharp disturbance in the surrounding magnetic field, a ripple that aligned perfectly with the optical brightening. This suggested that 3I Atlas might have expelled a massive burst of ionized gas all at once, momentarily coupling with the solar wind. In simpler terms, the object behaved like a natural capacitor, discharging stored electrical energy in one global flash. That would explain why the event occurred everywhere on the surface simultaneously. Once the electrostatic potential reached its threshold, the discharge could have cascaded across the crust at near instantaneous speed. If this model holds true, it would mean that 3I Atlas had spent countless years gathering electrical charge as it drifted through interstellar space, only to release it in a single blinding pulse when solar radiation finally ionized its surface. The hypothesis remains divisive, but it has gained momentum among heliophysicists, who note that similar, though far weaker, electrostatic discharges have been observed in ordinary comets nearing the Sun. None, however, have displayed the same scale or synchronized. Meanwhile, spectroscopic data from the Atacama Large Millimeter Array, ALMA, added yet another clue. Immediately after the flare, new molecular signatures appeared, including formaldehyde, acetylene, and traces of ammonia hydrate. These compounds form when radiation-processed organics are abruptly heated and interact with water vapor. Their presence suggested that the perihelion shock fractured the outer shell, exposing fresh subsurface material to sunlight for the first time. The pattern perfectly matched what scientists call a thermal snap, a phenomenon where extreme temperature differences create internal stress that causes a body to fracture from within. As 3I Atlas's crust cracked, volatile gases trapped beneath it would have vented explosively, releasing energy and molecules sealed away for millions of years. When the pressure finally stabilized, the brightness faded smoothly, explaining the steady decline that followed. Yet some researchers at NASA's Goddard Space Flight Center weren't satisfied with this explanation. They pointed out that the uniformity of the reaction couldn't be due to random fracturing alone. The synchronous timing across the entire surface hinted at a global trigger. Their model proposed a resonant effect. As the object rotated, solar heating periodically aligned with its natural vibration frequency. When that resonance matched perfectly, the stored mechanical energy released in a single pulse. If verified, it would mark the first recorded instance of a resonant thermomechanical event in an interstellar object. Still, the electrostatic discharge theory remains the most widely discussed, a model that, if proven correct, could redefine how we understand the behavior of interstellar comets. The indications of plasma activity were impossible to dismiss. During the brief outburst, instruments aboard the solar orbiter detected a sudden surge of high-energy electrons streaming outward from the object. The spike persisted only for a few seconds, but displayed a very distinctive pattern: a sharp rise, rapid decay, and perfect alignment with the object's trajectory. It strongly resembled the electrical signatures produced by discharge events in dusty plasma fields. If 3I Atlas's outer shell had been carrying an electrical charge, then the violent outburst at perihelion might have been the release of that stored energy in one massive global arc. For mission analysts, this discovery presented far-reaching implications. Could objects traveling between stars build up electrostatic charge as they move through galactic magnetic currents? And if so, could that energy influence how they behave when they approach a new star system? These questions have now become central to the study of interstellar visitors. In the days that followed the flash, telescopes around the world continued monitoring 3I Atlas without pause. The object's brightness stabilized but never fully dimmed. Its extended coma remained stretched out, and its gaseous makeup settled into a consistent mix of water vapor, carbon dioxide, and faint traces of organic compounds. Strangely, no visible debris or fragments appeared, no dust trails formed, and the core maintained a steady spin rate of about 8.6 hours. For something that had just undergone what appeared to be a planetary-scale discharge, it remained eerily composed. On November 2nd, the European Space Agency issued a preliminary assessment. It read, 3I Atlas experienced a sudden energetic release near perihelion consistent with internal gas venting or plasma discharge. No signs of material loss or structural breakup have been observed. In simple terms, the object had expelled a tremendous amount of energy, but gently enough to remain completely intact. The implications stretch well beyond this single body. If other interstellar travelers possess similar charged crusts, they too might experience comparable surges when illuminated by a new sun for the first time. Each such event could offer scientists a rare glimpse into alien chemical and physical processes that can't be replicated in Earth-based laboratories. Yet, the most intriguing element of the perihelion event isn't what it reveals about the composition of 3I Atlas. It's what it suggests about what comes next. Even after the flare faded, the object's luminosity never returned to its pre-encounter baseline. It stayed brighter, as if a long-term venting mechanism had been triggered. That steady emission implies the discharge didn't destroy 3I Atlas. It may have activated it. As it drifts farther from the sun, the object appears to continue releasing gas in faint, rhythmic bursts. Researchers are now carefully observing any subtle shifts in its trajectory and speed. If deviations emerge that can't be explained purely by gravitational influence, it would confirm that the perihelion event initiated a self-propelling outgassing process, much like a spacecraft executing a microthrust maneuver. By the first week of November, however, the flood of updates began to dry up. Teams that had been posting near real-time data suddenly went silent. NASA's Deep Space Network stopped issuing telemetry timestamps from the solar orbiter's plasma detector. The Minor Planet Center's photometric updates, once refreshed every few hours, were now arriving with multi-day gaps. Even the James Webb Space Telescope's raw imaging sequence of 3I Atlas appeared incomplete, with missing frames in its expected data. For the public watching this unfold, it looked as if the story had stalled, but inside research circles,
everyone knew the opposite was true. Something was unfolding behind closed doors. The first clear sign came on November 3rd, when the Space Telescope Science Institute unexpectedly restricted outside access to JWST's 3I Atlas observation files, citing priority analysis. Normally that label is reserved for planetary defense emergencies or potential impact threats, not ordinary astronomical curiosities. The move immediately fueled speculation. Researchers who had been analyzing the perihelion flare discovered their archive links had been revoked overnight. Insiders later confirmed that both NASA and ESA were coordinating a joint data review before making any further material public. Official statements attributed the delay to data verification, explaining that the event occurred under extreme solar interference, and that calibration checks were essential. But privately, many scientists suspected there was more to the story. Several observatories had reported low-frequency electromagnetic fluctuations coinciding with the flare, and those patterns were unusually coherent. If verified, such signals would require explanations beyond standard cometary physics. By November 4th, frustration within the independent astronomy community had boiled over. Avi Loeb of Harvard's Galileo project issued an open letter demanding full release of all 3I Atlas datasets. The foundation of science is transparency, he wrote. If 3I Atlas represents a new category of interstellar object, the global research community deserves unrestricted access to its data. Within a day, more than 80 scientists across 15 institutions had signed the appeal. Despite the growing pressure, NASA maintained its embargo, reiterating that data integrity needed to be preserved during reprocessing. The European Space Agency took a slightly more open approach, publishing brief telemetry summaries, but withholding all high-resolution spectral information. Their justification echoed NASA's low signal-to-noise ratios, could lead to misinterpretations if the data were released prematurely. Still, behind closed doors, astronomers whispered another theory, that the agencies weren't merely safeguarding data, they were protecting the narrative. Some privately wondered if the electromagnetic signals displayed any recurring patterns, something not easily explained as random plasma interference. To be clear, there remains no verified evidence suggesting artificial origin or deliberate control. The scientific community stresses yet secrecy inevitably breeds speculation. Online forums and research boards soon swarmed with theories, from directed energy bursts to deliberate maneuvering. Most claims were swiftly disproven, but the data blackout only intensified public curiosity. Independent observatories, meanwhile, kept working. Smaller telescopes in South Africa and Argentina reported faint irregularities in the object's light curve, possible indications of a slow change in rotation. However, without access to JWST's calibration data, confirmation was impossible. Then a leaked internal memo from NASA's Planetary Defense Office provided a new twist. Circulated through informal channels, it hinted that analysis was still ongoing into a mysterious 21-centimeter spectral coherence, a signal pattern that, if genuine, could carry extraordinary implications.